his initial ideas on these Berkovich spaces, these K-analytic spaces as he calls them, and then he wrote this IHES, this much longer IHES article. So this is a beautiful, you see it's kind of a big article, right? But it's much more expansive than the book, and the spaces in the article are in fact more general. And so let me just indicate what was the problem. The spaces in the book are in some sense not the right ones to work with. The complication is this. Once we glue these spaces together, it's no longer evident that every point in the gluing will have an aphanoid neighborhood. So the space will be created to be set theoretically to be covered by these closed sets. But you could imagine, I mean, if you're going to glue, this picture's kind of meaningless, but if you kind of glue these two closed sets together, and maybe you have some point like here, you know, in this space, well, the whole space, this whole guy is aphanoid, so of course every point in it has that whole aphanoid as a neighborhood. And similarly in this space. But in this glued space, it's not obvious what aphanoid neighborhood is going to exist around this point. Okay? And so this is sort of the problem that, you know, should points have aphanoid neighborhoods? Once you even define what that means. So should all points in the gluing have aphanoid neighborhoods? And this is perhaps the most serious distinction with the classical notion of ring spaces when you think about making schemes and every point should have an affine neighborhood, an affine open neighborhood. To make a good theory in which we glue these together, we have to give up this idea that every point should have an aphanoid neighborhood. Or at least if we want to have a theory so that reasonable kinds of rigid spaces can be promoted to Berkovich spaces, we should not expect that this kind of property should have to hold. Okay? The spaces that will have this property will have a distinguished name. They'll be called good. Anyway, they will show up later. But you should just keep in mind at the outset that because of the funny nature of this gluing with respect to the classical concepts of how you make ring spaces by gluing open pieces, since we're not quite doing that, we're going to have to give up this idea. So we now need to introduce the right topological notion. So we need, so I think they're called quasi-nets. So we need some topological concept to discuss maybe what we might think of as, roughly speaking, locally finite gluing along closed sets. And the picture that I usually keep in mind here, I don't know if it's really a good thing or not, is a pie chart like this. Here's your point, x, v1, v2, and v3. Okay? So what we're going to be looking for is a framework in which it's not going to be that every point has a neighborhood, an open neighborhood of some nice type, but rather it will lie inside of a finite union of nice things so that it lies in all of them, and the union of these is a neighborhood. So the individual VIs will be aphanoid. This will lie in all of them, and the finite union will actually be a neighborhood in the ambient space. Okay, that's going to be the sort of thing that we're aiming for. So let me first introduce this notion of quasi-net. So it's just a definition. So say X is a locally Hausdorff topological space. Oh, by the way, so what time did I actually begin? Does anybody know? 9:05? 9:06. Okay. Yeah, there you go. All right. So say I give you a locally Hausdorff space, and then a quasi-net on X is a collection tau of compact Hausdorff subsets. So you should think of like aphanoids, or these Berkovich spectra, so that, well, you have this kind of pie chart picture. So that for every point x in X, there are V1 up to Vn in this collection, so that X lies in all of them, and the union is a neighborhood of X in the whole space. Okay? So this is the basic notion that we're going to want to work with. And now what I want to do is define, if we have, so you want to imagine that a global Berkovich space should be it'll be a locally Hausdorff topological space equipped with a quasi-net with the property that each of the individual members of the quasi-net will be identified with some Berkovich spectrum, and then we want to somehow impose some kind of data that kind of glues them all together in a nice way. So it's roughly speaking
a Berkovich space or a K-analytic space is going to be a topological space X endowed with a quasi-net of aphanoids endowed with some kind of gluing data. So let's see how this goes. So, yes? No. Neighborhood, not open neighborhood. Just neighborhood. X is in the interior relative to the ambient space. So again, it's like in this pie chart. We have this space, and these are generally, in nice situations, these are all going to be compact Hausdorff. The ambient space might be Hausdorff, so this is going to be a closed set. It's a finite union. Okay? Yeah. Okay. So how do we sort of endow the global space with some kind of analytic structure? So say I give you X again as a locally Hausdorff topological space. And we want to ask, what do I mean by a K-aphanoid atlas? So this is going to be like, when you first learned, or maybe the second time, you learned differential geometry, there was these, before you knew what sheaves were, everything was described in terms of atlases. And you might have different equivalent atlases on this space, and there's some kind of maximal atlas. So we're going to define a sort of similar kind of structure using these quasi-nets. Okay, so a K-aphanoid atlas on X, so this is a quasi-net, tau on X, with two properties. First of all, there's some kind of stability under intersection. Okay? So if I give you two guys in the quasi-net, that if you intersect them, so if you look at all things in the quasi-net that lie in the overlap, that this is a quasi-net on the intersection. Okay? And the reason we want this kind of condition is because if you want to imagine that these are going to be something like aphanoid subdomains of the ambient space, we'd like to hope that when you intersect aphanoid subdomains, maybe it won't be aphanoid, but it should have some kind of an analytic structure. So it should be part of the collection of sets with respect to which we're going to be able to endow some kind of structure sheaf. So this is sort of going to guarantee that we can, in some sense, intersect reasonable domains and still have them admit some kind of an analytic structure. And the second ingredient, which is where all the substance is that to every member of the quasi-net, we're going to endow it with, roughly speaking, a sort of K-aphanoid structure. So for every member of the quasi-net, there is assigned a K-aphanoid algebra, A sub v, and a homeomorphism between its Berkovich spectrum and V, so that whenever you have an inclusion of members of the quasi-net, it corresponds to an aphanoid subdomain. So if you view this as M of AV prime inside M of AV, this is an aphanoid subdomain. Okay? This is identified with this is identified with this, that's part of the data. Okay? And that this should, in fact, be an aphanoid subdomain. So this is two collections of data. So this, maybe we'll say, to every V, I assign some A sub V. I suppress the mention of the phi, but as part of the data. Let me just call this script A. So you think about this kind of assignment as, roughly speaking, being like a structure sheaf on a base of opens. But these aren't really open in general, unless your space is a point or something weird. So that said, this is what we're going to call a K-analytic space. So a K-analytic space, or if Berkovich is far away, you call it a Berkovich space. This is a triple. So the space X, this quasi-net tau, and this sort of data, this assignment to every member of the quasi-net, you assign some aphanoid algebra. Okay? Now comes the subtlety, which is this is analogous to sort of defining manifolds via atlases. And so the problem is we need some kind of way to identify when two such structures on the same space are to be considered equivalent. All right? So when is sort of X a tau and X maybe A prime tau prime when R is the same. So let me give an example. Suppose A is k-aphanoid algebra, and X is the Berkovich spectrum. Here's a quasi-net. I hope, unless there's some set theoretic, no, not. Okay. So just consider just the whole space. There's your atlas. Okay? So tau consists just of the space X. Well, there's only one thing in it, so this is not a very interesting condition. Well, for everything in it, for X, there's this data, there's that, and, well, this is a vacuous condition, so we're in good shape. All right? But on the other hand, what if you consider instead tau prime to be the collection of all the aphanoid subdomains with the evident? Oh, okay, so now we have a notational disaster. Yeah, so, okay. So let me put a little dot down here. Sorry. So this is an aphanoid algebra. You see, I usually use a script here because I want to distinguish it from thinking about strict algebras. So it's not to be it's suggestive of this, but this is not the same thing as this. So in this case, there's only one thing, and A sub x equals A. All right? And similarly here, with the evident, I'll call it A prime dot, where again, A prime sub v is, well, it's just the usual coordinate ring of an aphanoid subdomain, U inside M of A. Right? This has some mapping property for some ring. Oh, sorry, let's call that A prime sub U. And we assign that ring. Okay, that's what this assignment is. So these are two different k-aphanoid atlases on the same topological space, but it's clear that they should be considered as somehow defining the same analytic structure, the same k-analytic space. So we need some kind of way to relate two different choices, in some sense giving us the same space. So in order to do this, let me just make a weak definition. Well, it's a strong definition, I guess. So a strong morphism. So of course, to talk about things being the same, you have to define what maps are. So this is a little bit of a technical story, so I'll just describe the basic idea. So what would I mean by a map from one of these guys to another? Well, the simplest case, like when you're dealing with manifolds, if, again, pretend you don't know what a sheaf is, all you know are atlases, the simplest kind of map to describe is a continuous map that carries every member of the atlas on the source into some member of the atlas on the target, and then you just require your map on those charts to look like a C-infinity map between open pieces of Euclidean spaces. Okay? On the other hand, the notion of atlas is a bit unwieldy precisely because there can be many interesting, like automorphisms, that might not carry members of the given atlas into other members of the atlas. And that's why you often have to pass to this maximal atlas. So similarly here, the first concept of map, which is not general enough, a strong morphism, is a continuous map of topological spaces so that for every v prime and tau prime, we call the map F, you have that f of v prime is contained in some member of tau, and for all such pairs, v prime and v, the map from v prime to v, you think about this as the Berkovich spectrum of some m of a v prime, and this as the Berkovich spectrum of some map AV, arises from a specified map of aphanoid algebras backwards satisfying a transitivity condition. Let me see what I mean by that. Well, let's see. I'm going from here to here, so the ring map should go this way, and this should be the induced map backwards. So this is a phi, and this is going to be the m of phi. Thank you. Yeah, let's put primes everywhere. There we go. Satisfying a transitivity condition. What do I mean by that? So we have two pieces of data. We have the continuous map, and then every time some member of this quasi-net lands inside one of these, there is assigned a ring map between the coordinate rings, which induces the given topological map. And the requirement is that if I have another aphanoid contained inside of here, Well, part of the data of this is an aphanoid subdomain, and so the corresponding ring map to this had better be the composite of the corresponding ring maps here. Okay, so you can sort of imagine that these ring maps might have to satisfy some kind of transitivity condition. This is, of course, not uniquely determined by that. Okay? Certainly, I mean, as we know from algebraic geometry, the topological space does not determine what happens at the ring level in general. Okay? So this is a kind of a lot of structure, and of course, one proves some lemma to the effect that to really define such a thing, you don't really need to specify it on all v primes. It's enough to specify it on a large enough collection to kind of cover this space, and you can kind of get the rest by appropriate gluing using the universal mapping properties of aphanoid subdomains. And let me just say that the notion of a morphism in general is defined by, let me just say, a slightly technical process. Which can be most easily described in terms of involving somehow gluing on enough members of an associated maximal atlas. A hat, tau hat. Given any one of these k-analytic spaces, there's a natural way to associate to this what's called a kind of a refinement, which is sort of a maximal k-aphanoid atlas. I won't define what this means, but if you work with these maximal guys, then you can get around this. This strongness refers to sort of this condition here. Okay? And this is too restrictive in practice. You can't demand that every one of these land inside one of these. As an example, if we come back here, yeah? I mean, there's sort of an obvious strong morphism from x a tau to x a prime tau prime, yeah? Because this has only one member in it, x, which is one of the things in here. So there's an obvious map this way, but there's not an obvious strong morphism backwards, because most members of tau prime don't land inside the unique member of tau, right? So you don't have a map backwards, so to speak. So if you refine things enough, you can sort of get around that. So anyway, suffice to say, if you work enough, you can define a reasonable notion of morphism, which you can construct in practice by gluing maps on aphanoids. And so in that sense, everything winds up working out quite nicely. And let me make one little remark, which is there are actually, I mean, this comes back to the subtleties in this definition of morphism, which is when we talk about a k-analytic or Berkovich space, in general we work with these sort of general k-aphanoid algebras. But of course, if you're going to be interested, as many people are, most interested in studying the k-analytic spaces associated to algebraic varieties, or perhaps to classical rigid spaces, then it doesn't seem clear that you necessarily need to work with an atlas involving these general k-aphanoids with these kind of arbitrary real numbers floating around. Maybe it should be enough to work with just aphanoids of the classical strict type originally considered by Tate. So we can define a strict k-analytic space is a k-analytic space of this type where AV for all members of the quasinet, this is a strict k-aphanoid algebra. Okay? Meaning no non-trivial real radii floating around. A classical k-aphanoid algebra. So roughly speaking, the general ones are obtained by gluing general aphanoids, again with this local finiteness condition, right? In the definition of a quasinet, I can't emphasize this too strongly, there's the requirement that every point has a neighborhood that's a finite union of members of the quasinet. So we give up on the idea that every point should have an aphanoid neighborhood, but we allow that every point has kind of a union has a neighborhood that's a finite union of aphanoids. Okay? So that's a general analytic space, but we can imagine sort of gluing strict classical spaces along strict overlaps, and that would give us the notion of a strict space. And now we have the conundrum that it's not clear that, and you can define morphisms in this world as well, only using strict aphanoids. It's not at all evident at the outset that you can have sort of strict spaces with their notion of morphism, and as a natural functor to general k-analytic spaces. it's not clear that this is fully faithful. Meaning, I could give you a couple of strict spaces, and maybe within them I find some non-strict aphanoids that cover the space, and I define a strong morphism or some other kind of morphism by using these more general kinds of aphanoids that are floating around. After all, even within the closed unit disk, there are lots of wacky aphanoid subsets with real radii floating around. Okay? So maybe you could define a morphism by starting with nice strict spaces, but gluing maps between non-strict aphanoid pieces. And it's not at all evident that such a map actually could also have been constructed from an atlas only using strict aphanoids inside. Okay? So it's not clear that strict spaces, if you have a map in this larger category, that they can actually be described only using stricts. As another example, suppose I give you a general aphanoid, and suppose it has a cover by finitely many strict aphanoid subdomains. Let's say with strict overlaps, just for simplicity. Is A strict? Okay? Is the notion of strictness local? So in fact, if you want to think mostly about strict spaces, but you'd like to work in this larger world, there are some actually quite subtle questions that need to be addressed. And fortunately, Michael Temkin has solved this conundrum very elegantly. This has only happened quite recently. But anyway, fortunately, the answer is yes. Okay? So in fact, after the fact, there is no ambiguity, but you have to just appreciate that at the outset, a priori, there is a real distinction here, but in fact, you can work with these within this larger framework, and actually there's no ambiguity at all. Okay, so these are the kind of the general spaces, and as I said, these strict spaces are of an interesting special type. Let's look at one more interesting example. So suppose I give you X, which is an algebraic case scheme. So some locally finite type scheme over our base field. And now you might want to ask, can we associate a Berkovich space to this? Okay? Much like in classical rigid geometry, if you've looked at maybe the exercises from my lecture notes, you could sort of associate, or the examples at least, you can associate a rigid analytic space to any algebraic scheme. Complex analytic geometry, you can associate a complex analytic space to any algebraic scheme over C. So in this framework, can we do this? So the answer is yes. And let me just say that there is an associated Berkovich space. X analytic. And let me just say it is characterized by an elegant universal mapping property. Very similar. I mean, this is described in Berkovich's IHES paper, but in universal mapping property, much like in the classical case. But let me not formulate it just yet, or not at all in this lecture. Okay, it's discussed in the notes. Actually, maybe it's not discussed in the notes. Anyway, it's discussed in Berkovich's paper. But one thing that should be emphasized is that in general, well, I'll just tell you what the property is. Here's your algebraic scheme, and you can consider for every K analytic space, you could consider a morphism of locally ringed spaces. So I have to clarify one point here over K. So K analytic space I defined using this sort of not quite structure sheaf data, something defined on quasinets. So because the topology is locally described, every point has a neighborhood that's a finite union of members of the quasinet, it shouldn't be terribly surprising, and it is in fact true, that using the data of this A dot, you can construct what you would call a structure sheaf on this space, meaning for every actual open subset of X, you can define a sort of ring of analytic functions by gluing the A sub v's for all the v's inside of that open set. Okay? So you can, in fact, endow this with a natural structure of locally ringed space. But I have to emphasize, unlike the case of schemes, morphisms of K analytic spaces are not defined as morphisms of locally ringed spaces. any map of k-analytic spaces does, in fact, have an underlying map of locally ringed spaces, but the k-analytic space has much more structure because you have data of functions on these closed sets, or at least these compact Hausdorff subsets. Okay? So these are not to be viewed as a subcategory of locally ringed spaces. So in that sense, it's a little bit more subtle than working with schemes. So viewing the k-analytic space as a locally ringed space, you could consider maps from a scheme, and then you could ask if there's a universal one. Is there a map to an analytic space so that all such maps uniquely factor through it? And the answer is yes. Okay? And in fact, this X is the set of what you might call all classical points of Xn, and this Xn is in fact a strict space. Okay? So the analytic spaces associated to algebraic schemes are in fact strict analytic spaces, and sorry? Oh, whoops. Yeah, good point. Right, because this has fewer open sets. Okay, let's do, sorry. So if we think about analytic spaces mapping to X, and then we ask if there is, everything was backwards. There we go. Okay, this has fewer open sets. Opens in here is Zariski open, should pull back to analytic open. Analytic opens don't know where to go back in there. So sorry about that. So if we have our algebraic scheme, we could look at maps from any analytic space to this, and we could ask if there is some final one, some analytic space mapping to it so that they all factor through that. Okay? Wait, something is disturbing me here. So this is, let's just cross out that statement. Okay. Yeah, okay, now it's fine. There's something is, oh, right. Okay, now, right, in the rigid case, this would be the set of closed points of this. Yeah, this was a nonsense statement because schemes have lots more points. Sorry, that was, forget I ever said that. Let's cross that out. Okay. So anyway, these are the basic examples of the strict spaces. Okay. Okay. So that said, another interesting class of spaces beyond the strict spaces are the good spaces. So a k-analytic space X is good if every point has an aphanoid neighborhood. And, well, of course, to make sense of that, what I really mean is, i.e., some member of the associated maximal atlas so that V is a neighborhood of X. That's maybe the simplest way to think about it. And as I mentioned at the outset, and I'm not going to give examples here, there are, in fact, k-analytic spaces that are not good, but the ones that come from algebraic geometry, so example, Xn for X, an algebraic k-scheme. So the ones that come from algebraic geometry are, they're always strict and they're always good. Right? But there are some other kinds of spaces out there, and as the, well, it's not really an example, but I'll just say that the good spaces, so the spaces of Berkovich's book, are precisely the good spaces, and then I think Deligne pointed out to him that the good spaces were not good enough. Okay, now if we want to really make constructions like fiber products and other things by sort of gluing, one needs to introduce a reasonable notion or a replacement for the idea of an admissible open set, or maybe or an aphanoid subdomain. So there's a general notion of an analytic domain. So a k-analytic domain, and again, this is in some sense the replacement for the concept of admissible open set. So a k-analytic domain in X, well, what should this be? Well, I want it to be, well, the idea of an admissible open is it should be a subset that has an admissible covering by aphanoids. And so it's sort of a similar condition. So as a subset, so that for every point in Y, there are finitely many members in the sort of maximal atlas so that that pie chart picture holds. So that Y is in all of them, and the union is a neighborhood. Oh, goodness, and they're all contained in Y. Neighborhood of Y in Y. All right? So every point of this has a neighborhood in this space, in this subset, such that it sort of lies inside of a kind of a finite union of aphanoids of the ambient space, and in fact lies in all of them. Okay? So this is a kind of an analytic domain, and the point is, as sort of is not much of a surprise, analytic domains are the kinds of subsets which we can endow with analytic structure. Okay? By kind of using the members of the atlas that actually sit inside of that analytic domain. So every analytic domain, so for example, any open subset, U in X is an analytic domain, but there are plenty of closed analytic domains. Okay? But also, there are lots of closed ones. And let me just say that the point of this definition is that analytic domains can be endowed with K-analytic structure satisfying a universal mapping property, much like the case of aphanoid domains. Universal property of set theoretic type, meaning maps of analytic spaces to X, which set theoretically factor through U, factor through it in the sense of analytic spaces. Okay? So once we have these analytic domains, the point of introducing these is by using analytic domains, you can then contemplate, you can do general gluing constructions. And let me just mention two examples. So two basic examples that one wants. First of all, fiber products, where in the aphanoid case, you just have the completed tensor product construction. So if I give you a triple of aphanoids, if you consider the Berkovich space, not just the topological space. So unlike for rigid spaces, where first we use this notation M of A, and then we use this SP notation when we think about it with the structure sheaf, for these K-analytic spaces, we still write M of the ring, but we really always now think about it as having this extra data of this kind of atlas with these rings of functions and so forth. So with this extra structure of K-analytic space, this, together with the evident maps of K-analytic spaces, I should have said, as maybe you were just assuming, it's quite reasonable to expect that, of course, the functor that goes from K-aphanoid algebras to the associated K-aphanoid Berkovich spaces is, in fact, a fully faithful functor. So morphisms between aphanoid spaces do, in fact, come uniquely from morphisms of the topological, of the Banach algebra, as you would hope, just like in algebraic geometry. So if I give you these two maps together with the compatible map down to the base, this is a fiber product. And then by doing general gluing of analytic domains, you can, in fact, promote this. You can make general fiber products. And similarly, by globalizing this construction of extension of the base field, you can define. See, now it's an actual fiber product. As I mentioned last time, Berkovich spaces have this very nice feature that a space over a big field, a ring over a small field, maps to a ring over a big field, but geometrically you actually have a map backwards, okay, which you don't have in rigid geometry. A rigid space over CP can't really be mapped to a rigid space over QP because the transcendental points don't know where to go. All right? But in the Berkovich setting, this is no problem. So you can define a larger category that contains all analytic spaces over all extensions of the base field, and in that sense, extension of the base field really does serve as a fiber product. Okay? So change of the base field is a much simpler operation in this category of these Berkovich spaces over non-Archimedean fields. But one warning, well, from the viewpoint of schemes, it's maybe not such a surprise, but from the way of thinking complex analytically, maybe it is slightly surprising. If I give you the map, if I give you a fiber product of analytic spaces, and you look at the underlying topological space, and then you look at the corresponding map as so, this is generally very far from being bijective, even if K is algebraically closed. because there are always non-classical points. No matter what the base field, there's always the Gauss norm in the unit disk, for example, and lots of other stuff. But in general, it is proper. It is surjective and proper in some appropriate topological sense. Okay? So now let me briefly describe a couple of basic definitions of classes of maps that are of interest in working with these analytic spaces. So for example, how about closed immersions? Okay? So let me just say that, so using k-aphanoid subdomains, you can define the general notion of a closed immersion from one k-analytic space into another. One way of thinking about it would be that for every member of the atlas here, the preimage should be a k-aphanoid in the maximal atlas of this with associated ring map that is actually surjective, and more generally, these are classified by, well, I'll say coherent sheaves. And of course, well, what is a coherent sheaf? I'm not going to get into the definition here for reasons of time. Let me just say that once you have this flexible theory of analytic domains, which replace the sort of theory of admissible open sets in the classical case, then these give rise to what's called a G topology. So some replacement, something analogous to the kind of Tate topology. And this includes not only things like aphanoid subdomains, it also includes open sets in the actual space, which may not be something that you can visualize in terms of the classical theory. And so a coherent sheaf is going to be a certain kind of sheaf on a topology defined by analytic domains. If you restrict your attention just to the ordinary open sets, then coherent sheaves do in particular give rise to ordinary sheaves on the topological space, but you can also evaluate them on a larger class of subsets, these analytic domains, like aphanoids, that may be closed and not open, and so that gives them their structure. Coherent ideal sheaves. Okay? So closed immersions are classified by coherent ideal sheaves on the target, much like in the case of classical algebraic geometry. And now you can go to town and carry over lots of other definitions. So for example, you could define separatedness, that the diagonal is a closed immersion. You could define finiteness. Preimage of certain aphanoids should be aphanoid with appropriately finite structure map, and so forth. But one huge warning, which is because of this issue with the diagonal, you see X, for example, maybe if you just look at the structure map, this can be non-separated, yet the underlying space of X may be Hausdorff. Because the diagonal X cross X as an analytic space, its underlying space is in fact much bigger than the ordinary topological product. And so the concept of separatedness refers to this space, whereas Hausdorffness refers to the topological product. So in fact, Hausdorffness in the underlying space is a much weaker condition than separatedness of the analytic space. Okay? So with that warning mentioned, let me briefly tell you what is the dictionary that relates Berkovich spaces and analytic spaces. So let's say we want to go from rigid spaces to Berkovich spaces. And if I give you X is a, let's first, for simplicity, take a quasi-compact and quasi-separated rigid space. Okay? So this is the data of, we have some aphanoids with overlaps that are quasi-compact, covered by, so finitely many because it's quasi-compact, quasi-separated, the overlaps are covered by finitely many aphanoids. Let's see, SPAIJ1 to SPAIJN for this overlap. And now if you use this, you might make a bunch of these, oops, not N, M, depends on I and J. You might make a bunch of Berkovich spaces, again with kind of gluing data. And so you get some Berkovich space X and. Not to be, this is regrettable notation, but it's standard, it appears. This is the K analytic space associated to the quasi-compact rigid space. This is not an algebraic scheme. Wouldn't make any sense for it to be unless it was a point. And so therefore, hopefully, there's not ambiguity. You could, of course, also write X Burke, but this is often not done. Anyway, what properties does this space have? This guy here is, excuse me, this is compact and Hausdorff. Okay? And so, in fact, in this way, one actually does get an equivalence between quasi-compact, quasi-separated rigids, and it's strict. Okay? This may not be separated, but this guy turns out to always be Hausdorff. And so, in fact, you can go back and forth. There's an equivalence of categories between quasi-compact, quasi-separated rigid spaces and compact Hausdorff strict K-analytic spaces. And let me just say that this can be generalized. You can extend this a bit to larger spaces. You want to allow things that are big, like algebraic schemes. Okay? So you can basically get rid of this condition at the expense of a local finiteness here, and on this side, you get rid of this, and you put in paracompact, whatever that means. Okay? So one does have actually a very nice dictionary between rigid spaces and Berkovich spaces, and in this setting, the rigid space is the set of classical-looking points of the Berkovich space, the ones whose completed residue field is finite over the base field. So having said these various things about these Berkovich spaces, let me show you one thing. So one can, of course, go on and define properness and flatness and discuss gaga and other things. So these are all discussed in the notes. But what I'd like to end with is to solve the question that I mentioned at the end of last time, which is to use Berkovich spaces to answer a question in classical rigid geometry. So let me give a kind of application. Of course, this application does not justify the entire theory. There are much more serious applications, such as the theory of étale cohomology, that do justify all the effort. But let me just show you by way of example how we can answer a classical question very intuitively by using the nice features of these spaces. So suppose X is a classical aphanoid space, and again, Z is an analytic set defined by some ideal, and U, containing Z, is admissible open in X. And the question is, and let's say I has some chosen generators, F1, Fn. The question is, do there exist some positive numbers, epsilon 1, epsilon n, saying the divisible group of the value group, such that this admissible open, in fact, contains one of the special type where the functions are bounded by these positive constants. So in some sense, so here's X, here's Z, and here's U. These kinds of tubes, defined by the F's being absolute value no more than some epsilons, are these a cofinal system of admissible open neighborhoods of Z and X? And as I said, if you try to prove this using classical rigid geometry, it's quite difficult, I think, or at least takes a long time to sort of figure out, and it's much more complicated than it ought to be. And so let me give the solution using Berkovich spaces. Okay, and we'll see if I can actually pull off the feat of fitting it into this little space down on the bottom of the piece of paper here. So first of all, without loss of generality, because this thing is quasi-compact, in fact, lose no generality by taking U to be a quasi-compact, and of course it's separated, admissible open. Okay, so it fits into the framework that was over here. The U and the X and the Z, these are all quasi-compact separated rigid spaces, so we're going to shift over to the Berkovich side. So an equivalent question, or let me just say enough to show that Z Berk, so I'll just write a B, is contained in the interior X Berk of E Berk. All right? This is a compact space. I'm sorry. Yeah. So I want to know, is this contained in the topological interior of this? Because the Berkovich space associated to Z is, in fact, the zero locus of these F's in this space. It is precisely the simultaneous zero locus. And so then you could use an easy topological, just a simple compactness argument. If this really lies on the interior, open in the space, then just by a compactness argument, you could get these epsilons that contain this. Okay? So the question is, why does this hold? Well, at the end of last time, I mentioned there was this theory of of relative interior and relative boundary in the aphanoid setting. Now this U is not aphanoid, so this guy is not an aphanoid space, but let me just say that, in fact, the concepts of relative interior and relative boundary can be extended to the Berkovich setting without aphanoidness restrictions. And in that setting, because Z to X is a closed immersion, and in particular is finite, the same thing holds in Berkovich land. So this guy is, in fact, its own relative interior with respect to X. And in general, if we think about Z included in U, included in X, there's a general transitivity relation for this theory of the relative interior, and so it winds up giving that this is the intersection of the relative interior of Z with respect to U intersecting with the relative interior of U with respect to X. But, in fact, because this U is a quasi-compact admissible open, in fact, it is an analytic domain within X. And just like last time I said, if I have one aphanoid subdomain and another, that the relative interior in the Berkovich sense is the topological interior, this holds more generally for analytic domains. And so, in fact, this relative interior here is, in fact, the topological interior, and therefore that solves the problem. Now, of course, I've hidden all the mystery of the theory of the relative interior, right? But the point is just to emphasize that the nice topological features of these Berkovich spaces, in fact, do provide enough technology to sometimes answer questions in the classical case in a way that accords very closely with your topological intuition. And in particular, and let me just again say, the reason why it was enough to show this is because, again, by a very simple compactness argument, compact in the usual topological sense, this interior containment does provide these positive epsilons precisely because this is the simultaneous zero locus in this whole space. So this is a very kind of toy example, but hopefully it conveys some sense in which the very nice topology of these spaces and the rich enough structure theory that one has concerning that topology does allow one to sometimes think about classical questions in this framework and actually answer them in a way that's much simpler than appears to be possible within that setting. Okay, so I'll stop there. Thanks. So, yes? Okay, so one could ask, if you want to describe a map between Berkovich spaces, do you have to really give it with all this sort of atlas stuff, or maybe is it enough to maybe just think about the underlying locally ringed spaces or the underlying G-topologized spaces? And I have to say, in all honesty, I've never thought about this question until a couple of days ago when somebody asked me a variant of this kind of question. And so the answer is, I have no idea. I would expect the answer is no, that there must be some weird examples where you really can't get away with ignoring some of the structure. But the way to definitively settle that is to ask Ofer Gaber. But probably he wouldn't answer, but you could try.